Hey all, so in this video I want to take a look at using the BD software's C compiler under CPM running on the IMSAI 8080 emulator from the High Nibble. The configuration I've got here of course is the IMSAI 8080 from the High Nibble. You can see it down there in the lower left hand corner. I have a High Nibble S-132 attached to the back. It'll be doing VT100 emulation. Its VGA output is being fed to a video capture device which is in the right hand upper part of the screen. You can see the flashing cursor up there. And I just wanted to really do a demo of reading and writing ports. So on the front panel of the IMSAI 8080 are a set of programmed input switches and a set of programmed output LEDs, and those are on port FF hex on the machine. And we're going to write a small C program to read the switches and display them on the LEDs on top. It's going to be a little more complex than that, and then I'm going to have a loop running in the software that'll count from 00 hex to FF hex, and it will AND that information with what it reads off the switches, and that way if one of the switches is down, like I've done there, we can mask that bit, and the LED will always be off. We can mask any bit or any combination of bits that we want to here, just to give it a bit of variety so we can see it run. So let's go ahead and get the IMSAI powered up. And we're going to do a stop and a reset and an external clear, and I'm going to run, and we should see the CPM prompt come up, and we have. So the machine's configured to the High Nibbles specification for running CPM22. I have the CPM22 disk mounted as drive A on the machine. I have configured this version of CPM for a full 64K. I think the version that ships is configured for 56K. There's a way to update it. Maybe we'll explore that in a future video to get the full 64K around. So we're sitting here with the A prompt shown. This is the CPM22 disk. There may be a couple other things here I've added onto it. I'm not sure. I have a hard drive image mounted on the machine, which is always drive I. We can see here at the root, there's a little bit of stuff here I've been playing with. If you're unfamiliar with how CPM deals with larger drives, as I recall, I know that the quote hard disk image I'm using here is a total of 8 megabytes of storage. It's really just a large floppy in the way the system sees it. It's the maximum size a floppy can be based on the capabilities of CPM on the machine as it currently is. There's effectively partitions on this floppy. I'm going to call them partitions, although they're really not. They are user space 0 to user space 15, and this is a way of organizing files into smaller groups. And the idea being in a multi-user system, you would see your set of files and not see others' files. So by default, we're seeing the files here for user 0 or partition 0, depending on how you want to think about it. I'm going to jump over to user 2 or partition 2. And this is where I have some C code in the compiler laid down on the machine. I have taken the TE editor, the text editor. I don't remember the gentleman who wrote it. It's available up on the web. I'll see if I can provide a link to where you can get it. I have modified this for my own purposes. I can't distribute it as I recall because I've taken away the attributions for the original author. I'll have to look. Maybe I put those back in. I've created two versions of the TEN editor. So TE narrow and TE wide. Wide edits in 132 column mode, narrow in 80 column mode. I'm going to use the 80 column mode here. That's why it's TEN. And I believe the source code is portio.c. This is a full screen editor. As you can see, it's got a little bit of color highlighting to it just to make things easier for me. And let's take a quick look at the source. So of course there's a comment up here at the top that basically says what I said, read from the program switches and output to the programmed output LEDs. Keep in mind this is a K&R style syntax. C compiler K&R syntax came before ANSI. If you've been programming in C and learned it in the last almost 40 years, you have learned ANSI C. And there's some subtle differences, especially around how function variables are defined in the system. I won't dive into that here, but be aware if you get BD software C compiler set up in your machine, you need to understand the K&R syntax. You'll need it. I've got a couple pound sign defines here. program switches on port FF and program LEDs on port FF. An out port to port FF will write to the LEDs, and an import will, of course, read from the switches. There's our main function, our entry point in the C code. I've got a variable I called A that's just a loop variable. This thing, like I said, loops from 0 to FF hex. There's a variable called I that is an integer, obviously, that is used to read the programmed input switches. We're going to loop indefinitely, so we're going to force it to just loop. We've got that counter that's going to run. In this case, I'm expressing it as decimal. It's going to start at 0, and it's going to run up to 255, the A less than 256. We'll keep it in the loop from 0 to 255. And after each loop, we're going to increment A. That's the plus plus A. Comment here, we're going to read the programmed input switches from the CPA, and that's what the I equals NP function does here. NP is a provided function in BDSC that allows you to read from a port. We now have the value of I. A note here is that the programmed output LEDs are inverted to what you think they might be. By default, if an LED is off, that represents a 1. If the LED is on, it represents a 0. That's just an artifact of how the hardware was designed. There is a mod that some people did to their CPA front panels to invert this. I'm going to leave this pure as it was on the IMSAI when it shipped. The way I fix this is I essentially invert the bits, and this 255 minus will invert the bits for me. So, you know, I've read the bit pattern from the switches, and if I subtract that value from 255 as an integer math, I will get the inverse, and the LEDs will then match what the counter is, and that's kind of what this comment here is trying to tell us. I'm going to write via the out port. Again, I supplied function in BDS software C to the program LEDs. I'm going to take the value that we read, which was I. I'm going to AND it with the switches, or I'm going to AND it with the loop counter, and that's where I take care of the only enabled bits that we want to see when the switches are in an up position. We're going to output that. We're going to display to the console output the values of, so the first value there is what we read from the switches. The second value is where we are on the loop counter. And that third value in the end will be the byte that we sent to the programmed output LEDs. I'm putting in a small sleep here. This is defined, again, it's a function provided by BD Software C compiler. I believe it works by machine ticks, meaning if you're running 4 megahertz versus 2, you will get shorter, I believe, loops at 4 megahertz. But this really is our demo program. This is all it does. So let's go ahead and escape out here. I'm going to exit. I didn't make any changes. I'm going to run the compiler, port.io. It's compiling it here. I believe I have the machine configured for a 4 megahertz C80. So that was compile time at 4 megahertz. We're going to do a C-link, port.io. It's linked. We can see we have the C source here. We have a CRL file that is essentially the compiled assembly from the C compiler output. It's what gets linked. The CRL files are what get linked together. And the final program, port.io.com. We run port.io. We'll see this start to work here, and we can see the loop running here in that second column. Its output is a hex value. We can see, looking at the IMSAI, for the programmed LEDs up here, there's no output, and I can enable that first bit by flipping that switch up to a 1. I can enable the second bit for display. So if we take and enable all of the outputs, we can see it doing a nice binary up count here. And so this really does demonstrate just basic port.io. We're reading from port FF to get the value of these 8 switches. We're writing to port FF to get these programmed output LEDs up high. And we can AND into that to control which LEDs we see displayed. So if we turn all the LEDs off, we can look at the least significant bit, and we can see it blinking with each count here. For one count, it'll be up or on. For the other count, it'll be 0, and that's because we're outputting, you know, an odd value and an even value, and this bit position has a weight of 1. If we look at the next bit being output, it's blinking at half the speed. That has a bit value of 2. So we've essentially taken the output, or that loop counter, and we've divided it by 2 and divided it by 4. It gets slower, and we can enable, like I said, any combination of bits. So let me go ahead and hit Control C here to get back to the CPM prompt. Let's go ahead and run TE wide here, the wide version, just so you can see it in action. Portio.c. It, as you can see, put the screen into 132 column mode. It's using the VT100 features of the S-132 VT100 emulator here to do that. And this gives us the ability to edit wider programs because of the limitations of the machine, 64K of RAM and the space that the editor takes, etc. I broke these up into 2 different programs just because it gives me back a few extra bytes so I can have a bigger source file. Let me exit out of that and jump back into the narrow version. And we'll just walk through the source code one more time together while this runs. Let me go ahead and enable. Well, it's not running in the background, thus whatever was written to this port last is all that's displayed. Right now these switches have no impact on what's displayed because the program isn't running. And we'll walk through this one more time together. A standard IO.H is a standard C header. You've probably included it in nearly every C program you've ever written, especially if it does console I/O. A couple of # defines for the port that the LEDs and switches are on. Loop variable, the input variable. From the switches, loop forever, count from 0 to 255, which is 00 to FF hex. Get the switch value, a little comment on why I have to invert it. We talked about that before. Output it to the port LEDs. Tell the user what we did. Sleep for a little bit of time here and go on to the next loop. So let's go ahead and comment this sleep out and see it run full speed. In this case, save the file. We're going to exit. We're going to CC port IO. We're going to C-link port IO. Now we're going to run port IO. And you can see that significantly faster. Again, it's a C program, so it's not written in pure assembly. It's got the C overhead. It's doing printf to get that output to the console. So, you know, it's running at the speed it runs. Same thing, we can mask off LEDs. That one's blinking so fast now that you can't see it being on or off. You can kind of see this one flickering. Hopefully it's showing up there on the webcam. It might be. That one's blinking a little slower. So remember, we're essentially the raw value out divided by 2, divided by 4. This would be a divide by 8, divide by 16 of that loop counter. 32, 64, and 128. And in that mode, you can see that nice binary up count from really bit 2 up through bit 7. Maybe from bit 1 to 7, depending on how good a job the camera's doing here. So where we're heading with this, just so you know what an upcoming video will be, is I'm going to plug in the D7 plus AIO. The D7, the D plus 7 IO, geez, I can't talk here. The D plus 7, I don't remember what the name of the card exactly is. It is a card that has digital and analog input and output on it that's emulated inside of the emulation. And that card is what allows the IMSAI with the S-132 card to do things like read analog joysticks. Because of the limitations of the hardware here on the IMSAI, it's not 100% emulation. And there's a few gotchas to know. And where we're headed with this is writing some software to control that card and control some input-output bits via that card and do some analog measuring and output from that card. So really, with that said, I think we've covered everything I wanted to cover in this video here. So I hope to see you in a future video. If you enjoyed this video, give me a like. If you're not a subscriber, I'd appreciate a subscription. You know, it always helps. The likes always help.